right, of the distributed algorithms that we introduced over networks, right? We showed that if the network topology is strongly connected and if the step size is sufficiently small, these networks are stable from the mean square error perspective, right, from the fourth order error moment perspective, and also from the first order error moment perspective. You remember these results? So we have established that if you choose a sufficiently small step size, the network is stable. Okay, the error moments will remain bounded within small regions whose sizes depend on the step size or the square of the step size. Okay, so what we are going to do in this lecture, mainly in this lecture, and then we will continue in the next lecture. Now we are going to assess performance. Now that I know that the network works, what kind of performance can I expect from the network? How well will it work? I'm not only interested in knowing that it converges, but how fast it converges and how close it gets to the optimal solution. So that's what we are going to do in this lecture, okay? So this material is based on chapter 11 from the text that you have there, which again you can download from my website. Okay. So this is reminding you what we did, right? So this is one of the results that we proved in the previous lectures, that if you look at the mean square error at any agent, that mean square error is going to enter a small region whose size is in the order of the step size, right? So, okay. So what I want to do now in this lecture and continuing into the next lecture is to find an expression for that mean square error. And I'm not only interested in knowing that it is of the order of mu, because the multiplying constant can be very, very large, right? I would like to know, give me an idea what that multiplying constant is. So we are going to derive an expression for the mean square error that will look like something like this. Mu max times something, right? Plus higher order terms. This is little o, so higher order powers of mu, right? So if the step size is very small, this term will be negligible, and we end up having that this term that we are going to find will determine how well my network performs under small step size conditions. You understand? This is what I'm aiming for, okay? It will take some effort until we arrive at the expression that should go inside this circle, but that's what I'm aiming for. I'm going to be much more explicit, find out what the right-hand side is, write it in this form, ignore that term because this is higher order in mu, and tell you this is the performance for small step sizes. Fine? This is the strategy, okay, for this lecture and the next. Okay? So before I get there, let me remind you of this concept which I introduced when we studied single agent adaptation already. Okay, so what we are going to do is, if I pick any agent, so this is just written generically, so you could think of this as W tilde K comma I for agent K. We are going to show that the lim sup of that variance has this form, some step size mu max times some constant, I'm calling it MSD bar, okay, plus higher order terms in mu, and I'm also going to show that the lim_inf has a similar form. Remember that we showed this for single agent adaptation. I'm just trying to remind you that a similar concept will repeat itself here. And remember what the lim sup result tells you essentially is that if you plot the variance as a function of time, as time progresses towards infinity, that variance will enter a region that's upper bounded essentially, right? This upper bound here is of the order of this quantity that you have here, right? That's what the lim sup essentially is saying. You may not converge to an actual limit, but it will be upper bounded. This is the smallest upper bound that you can get on this curve. And the lim_inf is from below, right? That's what these quantities show. So similar things will be shown for the network as well, for every agent K. We are going to show that the lim sup and the lim_inf satisfy relations similar to this. Now, why is this useful? Because now, if I take, for example, this quantity here, you can see this amounts to an expansion in powers of mu, right? The first term is first order in mu. The other terms are higher order in mu. So now, if I take that lim sup and divide it by mu, and take the limit as mu goes to 0, what will happen? The higher order terms disappear, right? And then I multiply by mu again, I recover this part, right? So that calculation, if I do it both for the lim sup and the lim inf, divide by mu first, and then add the mu again, right? Divide by mu and take the limit as mu goes to 0. Both of them will converge to the same limit, right? The lim sup and the lim inf will converge to the same value when mu is sufficiently small, right? Okay? So, motivated by this, if I take and multiply this again by mu, right? If I multiply it again by mu, what do you get? That quantity, mu times MSD bar, right? So, what this is suggesting is that this calculation that I'm doing here allows me to recover that first order term that I'm interested in, right? If I can do this calculation, find what this lim sup is, scaled by mu, right? This is the variance is scaled by mu, and then you undo the scaling. So if I can do this calculation, it gives me the first order term that I'm interested in. You understand? So that's why you are going to see in the derivation, you are going to see limits like this, but this is where it comes from, okay? Very often we simply write this expression in this form here just to keep it simple, okay? That we replace the lim sup by a limit, and essentially we say this 1 over mu cancels that mu. So very often we just say this, even though technically speaking this limit does not exist. The lim sup exists, but the limit itself may not exist, okay? But it's not uncommon for you to see this notation as well. Sometimes I may write it like this, but what I mean when I write this is that technically I'm evaluating this limit. Okay, fine, very good. So yes.
How sure are we that the higher order terms, they are smaller in magnitude as compared to the first order terms?
So when we get into the derivation, you're going to see how they compare. Okay, so the higher order terms, they will depend on a higher order power of mu. Let's say the first term is first order in mu, the second term may be second order mu squared. So if mu is very, very, very small, you can ignore that term in comparison to the first term, okay? So when we go through the derivation, you're going to see that power there, okay? So you understand the definition of the MSD, where it comes from, right? So don't be alarmed by this expression. It's very simple, right? But that's, okay, if this confuses you, think of it like this, okay? But this is the more technical way of getting it, okay? Very good, right? So here it is. That's why for every agent, so I write now distributed to say I'm interested now in the distributed solution. And I write the K just to say I'm interested in the MSD for every agent, right? For every agent, that's all. So I'm doing the same calculation for every agent K. And if you average over all agents in a network, I'm going to define that as the MSD of the network. Fine? Now, one interesting result that will follow, so I'll tell you what will follow before we get there, is that over a network, even though different agents may be subjected to different noise conditions, the data that they see may be of different quality, you are going to see that the network has an equalizing effect on the agents. The MSDs will essentially be uniform across the agents. Okay, so you are going to see that effect, okay? But for now, let's define it as a function of K and evaluate it, okay? Very good. So let me remind you of the conditions that we usually impose. You have seen these conditions before. I'm just reminding you now. And these are the same conditions that we impose in the single agent case as well, and in the centralized case as well. You are going to see the analog of that here. Okay, so you have seen these conditions. This is just a reminder, okay? So what are the conditions? First of all, when we run the stochastic gradient algorithms over the network, I'm using an approximate gradient rather than the true gradient, right? I'm using an approximate gradient rather than the true gradient. The difference, we call it gradient noise, S, right? So this is gradient noise at agent K at time I, okay? And I also introduced this notation, the calligraphic F, to mean this is the history of estimates up to this time instant, okay? So when I condition on F, it means I'm computing an expectation conditioned on knowing all the omegas that happened so far. Okay, so this is just the shorthand notation. Omegas all time up to I-1 across all agents. Okay, so everything that happened so far when I condition on F, I'm conditioning on that history. Okay, this is notation you have seen. Okay, now because I'm dealing with the general complex case, we always extend our variables, right? I explained this before because the Hessian matrices, they are not necessarily block diagonal. So if you want to capture exactly or accurately how error evolves over networks, you have to work with extended vectors, right? Extended W tildes, extended gradient noise vectors. So here it is. This is the gradient noise at agent K. You extend it to size 2m by adding the star transpose, right? That's all. If your data is real, you don't need to work with this, right? If your data is real, you just work with the top part. You just continue working with SKI without the E, okay? Now, since your gradient vector is extended, its covariance matrix will also be extended, right? Okay? So this is it. This is the definition of the covariance matrix conditioned on the data up to that time. Okay, so this is a conditional covariance matrix. So in effect, this definition here is a random variable itself, right? When you condition on F, it is a random variable because it will be a function of this F. Fine. Okay, so this is the gradient noise definition. Okay, so now with the gradient noise, we associate, just like happened in the single agent case, in the complex domain, we associate two limiting second order moments. One is the covariance itself, equation 8. You see, S star is the covariance itself, right? Because S is a complex valued random process in general, S times S star. So this, I call it RS, right? So this matrix is Hermitian and non-negative definite, correct? Okay. And this is the other second order moment where you have S and S transpose, right? This matrix here is symmetric, but it's not necessarily non-negative definite, right? So in the complex case, you need both RS and RQ. If you are dealing only with real data, we don't need to work with RQ. We just work with, right? In the real data, this would become SS transpose, but we still call it RS, right? Because I use that notation for covariance always. RS is the covariance of the noise S, right? Okay, and these are, I'm assuming that these limits exist, and I showed you before, right? Logistic regression, mean square error cost, quadratic cost, that these limits exist, and I told you exactly what they are. Okay, so in the limit, so this is the limit of these covariances, okay? I'm calling them RS at agent K, RQ at agent K, because if you go back to the definition, you see this here. What is the covariance of S extended at any time I, right? It will be the expected value of this vector times its transpose, correct? So this would be 2 by 2, a 2 by 2 block matrix, right? Correct? Because it will be, let me just write this compactly, S star transpose, and then you have to multiply by the star of that. So S star, S transpose under expectation, right? This is what has to go here, correct? Okay, so SS star, so this is what will go here, SS star, right? And then S star transpose with S transpose, so that's like SS star transpose under expectation, correct? And then you will get SS transpose, and then here, SS transpose star. So you see, this is for any time I, right? So you see that for any time I, the covariance matrix of the gradient noise involves these two types of moments, SS star and SS transpose. What you have below are transpose, right? Okay, so what I defined on the next slide are the limiting values of these two. As I goes to infinity, right? For any time I, okay, for any time I, there will just be RS, K, I, RQ, KI without a limit, right? For any time I. So here what I'm saying, when I go to the limit, I'm assuming that these limits exist, okay? Because the performance of your network will depend on these limiting values. For quadratic costs, if you go back, and for example, logistic regression, if you go back, I told you exactly what these quantities are, and I believe perhaps in one of your homework problems you also evaluate what these quantities are for logistic regression, right? Okay. So I'm collecting these quantities into this compact notation because the performance will depend on that. Okay? So this is the Hessian matrix at the optimal solution that the network is converging to. We already know it's converging to from the previous lectures. So the Hessian matrix at agent k, I'm calling it H sub k. What's the size of H sub k? 2m by 2m. Okay, and these two matrices that were defined in the limit, which I claim will determine the performance, I'm collecting them into a big matrix G. I don't want to be referring always to two matrices. Put them together because the covariance I just showed you how to compute, if you take the limit of that, in the limit it becomes this matrix, right? Okay, R, the transpose, Q, and the transpose of it. Call it G, okay, for gradient noise, G, okay? So you are going to see that the performance of your network, that quantity which will multiply mu will be defined in terms of three things. This H, of course, it will involve a sum over the agents because each agent has a G and has an H. Of course, the H's could be the same across the agents. For example, quadratic costs where the RU is uniform across all agents. The H's will be uniform, right? This could also be uniform. So there can be cases where the G's and the H's are uniform, but for generality, what will multiply the mu there will depend on a sum, okay, or will be a combination that involves the H's across the agents, the G's across the agents, and what else? The step size is there, right? So this adds information about the cost that you are trying to minimize. This adds information about what's interfering with your solution, the gradient noise. There is still one element that influences performance, that's the topology, right? The topology will be reflected in this expression by the P's. So you see the expression will depend on these three quantities. I just have to show you what expression is that. So that will take this lecture, maybe some of next lecture, but that's where we are going, okay? When all is said and done, this will be the conclusion. I will tell you exactly what that is in terms of the P's, G's, and H's. And once you have that expression, then you can compare how different networks perform in relation to each other, because for different networks you may have different P's. They may have the same H and G but different P's. Then you can say which topology will give me best performance, okay? You understand where we are going? Okay. So again, remember, the H is non-negative because it's a Hessian, and the G is also non-negative because it's a covariance matrix, okay? And because we assumed that my cost, what is the global cost? It is the sum of the individual costs. We assumed it is strongly convex, right? So it's Hessian, which is the sum of the H's, is strictly positive. The Q's are positive numbers, so obviously the sum of the Q times the H's will also be strictly positive, okay? So this condition holds because, why I'm saying this? Because in this expression that I'm going to tell you, this quantity will appear inverted, and you will need the trace of that. So the inverse exists. That's all. So this is saying when you see that inverse, don't worry about it. We know it exists, okay? So I introduced the gradient noise model. So this condition also, okay? So what condition do we need on gradient noise? Of course, apart from the usual conditions that we used in the previous lectures, like saying that the noise, the mean value of the noise is zero mean, the variance of the noise, the second order moment or fourth order moment, they are bounded by terms that these conditions are assumed because under these conditions my network is stable, right? So these conditions are assumed. Okay. In addition, I will need this condition to be able to derive the performance expression just like we did for single agent case and for centralized solutions. We need to assume that the covariance of this noise, this 2 by 2 block matrix I defined, is sufficiently smooth. Again, these results were shown for quadratic costs, for logistic costs. We showed this before, okay? The same thing here applies, okay? Now, what does this say? All I'm saying is that if you move a little bit away from the solution, right, this gradient noise. Now, gradient noise is determined by your choice of the approximation of the gradient vector, right? You are the designer. You pick what approximation you want to use. If you are reasonable and you pick a reasonably good approximation, the gradient noise will tend to be smooth. Right? If you pick a very bad approximation for the gradient, right, vector, then the gradient noise that results from it may not be smooth enough, may not satisfy a condition like this. So this is essentially a reflection of how well you did in picking your approximation for the gradient vector, right? That the gradient noise is reasonably well behaved. And I showed you for the logistic regression and for quadratic costs, the approximations we picked are well behaved in this sense, okay? So this is simply saying that if you move a little bit, it doesn't change much. It just changes by proportion to that step. And this gamma is some value between 0 and 4. You will see why we need it to be between 0 and 4, okay? Now, in the single agent case, I showed you, and exactly the same proof will apply here, that if this holds, actually a more general condition holds. Okay, if this holds in moving from the optimal solution to another value close to it, actually this more general result holds. You have that this Lipschitz type condition holds more generally. For any arguments, that difference will be upper bounded by a quantity like this. We proved this in the single agent case. Exactly the same proof holds here, okay? Starting from the previous condition, you can show that the previous condition assumed, right? The previous condition assumed that if I move from here to there, this is bounded by the norm of delta omega to the power gamma. The argument I used earlier in the single agent case, just repeat it, it will tell you that actually this difference is bounded not just by a gamma power of the norm of the difference, okay, but also by another term which is a quadratic term, okay? So what's the difference between this bound and the previous one? This one holds generally for any phi and omega star. The other one was local. So from that local condition, actually the gradient of the noise satisfies this more global condition, okay? It behaves in this manner, okay? We proved this before, okay? I did it here in class. I'm not going to repeat it. But I'm going to use this in my derivations, okay? It doesn't matter what these constants are. What's important is that they exist, okay? So how I'm going to use this whenever I face this difference, because I don't know what these are at time I. I can replace them by powers like this. And remember, errors, I know how bounded they are in the limit, because this is what we did in the last 3 lectures, bounding these errors, right? So whenever I'll have quantities like this that I don't know exactly what they are, I can replace them by bounds that depend on the errors, and then in the limit I can bound these errors, okay? Very good. So now, first result that I need to prove today, which I will need for the performance expression. The first result is this. Because of this smoothness condition that I just imposed, right, which I said holds for important cases, okay, remember what was the JK? The JK was the covariance of the gradient noise in the limit. Because of the smoothness condition that I imposed, and because I just explained that that smoothness condition actually holds more globally, you can now show that actually at any time I, the covariance is very close to that value by some amount that you can bound. You understand what this is saying? This is not only the covariance in the limit, actually for any, sorry, not for any I, for long, okay, not for large enough I, okay, for large enough I, so I, okay, after some large enough I0, for all moments beyond there, your covariance already is very close to G by a small amount. You know, if you think about it intuitively, it makes sense. In the limit, this is the covariance. And the smoothness condition says if I'm very close to the limit, the covariance, right, satisfies a Lipschitz condition which is bounded by the size of the error, and we know that the error is small, right? So it makes sense to expect that this is true, but we have to prove it, okay? So let me prove it. Now, from 14, I will conclude, this is the statement of the lemma. The trace of this is that, right? This is the covariance. When you write it like this, the expected value of the norm squared, it is the trace of the covariance, okay? Here I'm saying that the covariance is this plus a number of this size. So this is mu remember, this gamma is between 0 and 4, okay? So the minimum of that will come here, okay? Now, because of that, okay, I'm going to show, I can conclude from this that the trace is bounded or is close to the trace of this. That's essentially what this is saying. The trace of this is close to the trace of that. And the difference is, of course, of that size. That's what this is saying, right? Okay, so let's prove it. Okay, the argument is not difficult. Let's prove it. Okay, here it is. I actually proved this in the single agent case. I'm going to repeat it so that you remember it in this case, okay? So this is the covariance that I'm interested in, right? Okay, I'm actually interested in the actual covariance, not in the conditioned covariance. But let's start with the conditioned covariance. You will see why. Okay, so all I did, okay, so this is it. Here it is again. I did not change anything. I just added and subtracted the same term, first line and last line. This is the covariance at the solution. Nothing changed, right? Very good. Okay, but now, okay, this quantity here, by definition, is the covariance of the noise at agent K at time I, right? Okay, here it is. You see, this is it. I'm just writing it now more compactly, right? Rather than write this entire thing, right? This is the covariance at node K at time I, correct? This last expression is the same thing. It's the covariance at agent I at time I, right? This one is at phi, this one is at W, correct? Of course, the first one is the same thing, but I'm going to keep it like that. Okay, so I kept the first term, but the last two I wrote them as the difference of two R's. Why? Because I have a bound on the difference of two R's from the assumption, right? Okay. And that's why I conditioned here, because the R's, these R's are conditional expectations, okay? Very good. Now I'm interested in how far the covariance is from G, so let's subtract G. Okay, so if I subtract G from the left, I subtract it from the right. So here it is, I subtracted it, correct? I subtracted G, so subtract G and subtract G here. Correct? Nothing changed. Take expectations again. Correct? So for the first expectation, you remove the conditioning, right? That's what it does. So that's the first line. Correct? For the last expectation, here it is. And for the middle expectation, I kept it as it is for now. Okay? Fine so far? So it's just, I just add and subtract equal terms. I didn't do anything fancy so far. Okay? Okay, so now let's look at the norm of the difference, right? The norm of this difference. Because that's what I want to show, that this is a small, right? I want to show that it is a small. Okay, so the norm of this difference will be upper bounded by the norm of this plus the norm of that, correct? See, norm of the first term, norm of the second term, upper bounded, right? Now here, I can apply Jensen's inequality. The norm of an expected value, right, is upper bounded by the expected value of the norm. Correct? So that's what I did in going from this to that. That's all. Correct? Very good. But this one, right, I know that it is bounded, right? From the smoothness condition, I know that this is bounded, right? So let's see. Okay. Okay, so let's take the limit. So what I'm doing now, before that, let's take the limit. So now if I take the limit as I goes to infinity, right? I get the lim sup of this difference. Here it is. Okay. There is a typo, right? An E is missing here. Correct? You see E. Okay. There is a typo. Okay. Now, so take the limit. Okay. What is this limit as I goes to infinity? 0, because by definition G is that limit, right? So I get that the lim sup of this is the lim of this as I goes to infinity, correct? Okay, so you get that. Okay, so far so good. Remember, I'm trying to bound this. So let's find out what this is. Well, I have the bound on this, right? I have the bound on this. Okay, so let's look at that. Here it is. I know that this is bounded by the difference, right, to the power gamma here and to the power 2 here, correct? By assumption, okay? This is the difference, right? Fine so far? Okay. But remember, in the distributed solution, right? In the distributed solution, okay, we have bounds on, in the previous lectures we showed, where the variances of W tilde go to, right? Not these quantities, but these quantities are related to the W tilde, so let me show you that. Because remember, phi tilde is some combination of the W tildes using convex combination coefficients, correct? Okay. So, if I go there, okay, so here it is, you see. So let's look at this norm and at this norm and relate it to the norm of W tilde squared. That's what I want, okay? So here it is. So that norm at agent K, I replace what phi tilde is here, correct? Again, Jensen's inequality, right? Because these A's are convex combination coefficients, right? And this function here is convex, correct? So this is upper bounded. I can bring the A's out. So here it is, the convex combination of the norms is squared, right? This is Jensen's inequality. But all these A's are bounded by 1, so I can remove them. All I need is a bound. So I remove them here. You see, they are not here anymore. Okay? Very good. Of course, this is a sum over the neighbors. Of course, this sum is smaller than if I add over the entire network. Correct? Okay? Well, each one of these, I already know, by the way, each one of these is of the order of, under expectation, right? Is of the order of mu max, correct? So n times mu max is still of the order of mu max. So that's how I'm going to conclude that the expected value of this is of the order of mu, correct? That's this term here. You can repeat the same thing for this term now. How? Okay. To show, similarly, here I show that this squared is bounded by that, the sum of the norm squared. You can similarly show that this to the power 4 is bounded by that, the sum of the fourth power. How? Okay. Remember that this gamma is between 0 and 4, right? I think it is strictly larger than 0. Okay. So look here. Okay. So this function, if you plot this function over positive values of x, for values of gamma between 0 and 4, it will be an increasing function between 0 and x. For example, when gamma is 1, just so that you see, when gamma is 1, you will get x increases, okay? When gamma is what? 2, you get square root of x. It will also increase, okay? So this, okay. So why is that useful? Because this is what I'm interested in, correct? I can write it as this norm to the fourth to that power. But this is a function, right? This is this function here. Okay? So this is upper bounded, right? So this is upper bounded by what? It is upper bounded by sorry. Oh, okay, so here, if I evaluate the same function at a larger number, it will be larger, right? That's all it's saying. Because this is larger than that, okay? How do you prove this? Using the same argument from the previous slide, because this function here, x to the power 4, is also convex, right? Okay, so this argument is larger than that. So this function evaluated at this argument will be smaller than this function evaluated at a larger argument because of this property, right? Okay, so using this, I was able to conclude that this is bounded by that. But again, each one of these is bounded by mu squared from previous lectures, right? So, okay. So when you put these things together, here it is. So this will be bounded by the sum of the norm squared and the sum of the norm to the fourth to the power gamma over 4, right? Okay.
Why didn't we just bound the norm of W raised to the power gamma? Why did we have to take the...
Which norm?
W tilde raised to the power pi 4 outside and then raise 5 to the power 4?
Here, just because I wanted to use this property, because I know that this fourth power of this error is bounded by that, okay? So I wanted to use that property, okay, to relate this to the fourth power of W tilde because I have bounds on the fourth power of W tilde. That's why I wanted to introduce the fourth power of W tilde. If I put the gamma power of W tilde, I don't have a bound on it. I only bounded second and fourth order moments in previous lectures, right? So you will see this type of trick repeat. Often I have norms of errors. I try to relate them to errors that I know how to bound. Second order moment or fourth order moment. This is one example where I did that, okay? So the arguments are not difficult, but I'm going slowly so that you see them, okay? Very good. So let's put things together. Remember, I need to find this limit, okay? This limit, correct? Well, I just bounded the right-hand side by this sum and that sum. So under expectation, this is the expectation. Fine so far? Okay. Well, this one I know that it is bounded by mu, correct? Okay. And here, okay, so you see, so here I'm applying Jensen's inequality to this function here, right? Because here you have the expected value. What you are seeing here, you have expected value of something like this, right? X to the gamma over 4. And I'm saying this is upper bounded by expected value of X to the gamma over 4, right? This is what I'm using there because I can apply Jensen's inequality here, okay? Okay, that's because, like I say here, this function here, x gamma to the 4, it is concave over that, okay? So that's why the inequality goes in this direction. And that's why, by the way, we limit gamma between 0 and 4, okay? This is where we use it, okay? Between 0 and 4, okay. Well, now everything is done, right? Look here. This is of the order of mu. What about here? This is mu squared, mu max squared, right, to the gamma over 4, right? So this will be mu gamma over 2 from here and mu from here, right? Now, so what would be the ultimate result? It depends on which one of these dominates, correct? Remember that gamma is between 0 and 4. So if gamma is between 0 and 2, which one of these will dominate? This one will dominate, right? And if gamma is between 2 and 4, which one would be larger? Mu. Okay, so here, this should be the answer. Here, this should be the answer, right? So that's why we are going to write it as mu to gamma prime over 2, where gamma prime is defined as the min of what? Gamma 2. So you see here, when gamma is between 0 and 2, the minimum will be gamma. So you get gamma over 2 as you should. When gamma is between 2 and 4, the minimum will be 2. You get 1 as you should, right? Okay, so this idea of defining the exponent as the min of some arguments will appear a few times. It comes from arguments like this. Just because you need to determine, you will have several powers of mu, you would like to know which one of them dominates, it will depend, okay? So now we are done, because what have we shown? We have shown that this limit is of what order? This order. That's exactly what we wanted to show, correct? Understood? Okay, so we showed this is the first statement of the lemma, that this covariance is this plus something of that order. That's what this lim sup is saying, okay? Now you can transform that into the trace. How do we transform that into the trace? Okay, for example, if your X is a Hermitian matrix, it holds, this is not difficult to show, okay? It holds that the trace of X, okay, for any square matrix is upper bounded by the norm of X by some constant C that's independent of X. This is a homework problem. It's not difficult to show this, okay? So the trace of this, okay, the absolute value of the trace is exactly this quantity, right? It will be upper bounded by some constant times that norm. So it will be upper bounded by some constant times this, which is the same thing, correct? Okay, from which you get the second statement, right? That this quantity is close to that within that, or it is this plus that or this minus that, right? If the absolute value is like this, correct? You understand this? Okay, so we proved this first lemma. So let me go back to the lemma just so that you remember, because I'm going to use it. All I did is show that in the limit for large enough I, the covariance of the noise can be approximated by G, but I know exactly how good that approximation is by some power of mu, and I know that exactly, right? And not only that, the trace of that covariance, I can also approximate it by the trace of G, and I know exactly what that difference is, of what order I mean, right? Because what is going to happen next when I'm going to derive the performance expression, in the process of deriving the performance expression, the covariance of the noise will appear because it is in the algorithm. So I'm going to replace it by this plus that, right? Working with this is a constant, I can continue, and this will determine this will end up giving the higher order terms that I told you about that we are going to ignore. This quantity will end up going into the higher order terms in general, okay? Fine, so you understand this first result? Okay, so let's move on. Okay. So now I need to evaluate this performance metric, right, which I defined before. This is for the MSD, mean square deviation, right? Scale by mu and then recover the mu, fine? So this is one performance metric I would like to evaluate. There is another one, right? Excess risk. We did that for single agents also, right? This is mean square deviation. This is measuring how close your estimate is to the optimal solution, right? Another metric which is useful, for example, in machine learning applications, that metric tends to be more relevant. You are interested in knowing not how close W gets to W star, but how close the risk at W gets to the risk at W star. How close the minimum cost is the cost is getting to the minimum it can be. The risk value is getting to the minimum it can be, okay? That's measured by the excess risk. So let me define that, okay? Okay, very good. So this is just reminding you, okay? I'm just reminding you here what the omega star is. The omega star is what these errors are measured relative to, right? I'm reminding you, okay, that this is the aggregate cost, the sum of the individual costs. This is the weighted cost where these Q's are defined in terms of the P's, right? Here it is. A2 times P, this is the Perron vector of the matrix capital P, which is the product of the three A's in the general case, right? In the general case. In general, we don't need to be so general, but we are doing it here to capture all algorithms in a single derivation, consensus, diffusion, non-cooperative, centralized, and so forth. And these are the step sizes, right? So omega star is the Pareto solution, right? Is the solution to this. Omega 0 is the solution to that, right? Okay. Remember that when I introduced the weighted covariance, the weighted cost, I introduced it in two forms. One was this form, where I said, let's use weights, the Q's that come from here. In another form, I said, let's take these Q's and redefine them, normalize them. Take the Q's and divide them by the sum of the Q's. Remember, those Q's are positive numbers, right? And you have n of them. If I divide each one of them by the sum of all and replace this by a Q bar, the minimum does not change, right? But the advantage of that is that these Q bars now add up to 1, correct? They add up to 1. Okay? So this is what I'm saying. So why I'm doing this? Because I'm going to use this normalized definition to define the excess risk, and you're going to see why very soon, okay? So it doesn't really matter. The algorithm is minimizing this, is minimizing that, okay? But here, these Q's are normalized, Now, the advantage of working with this is, for example, if all the JKs happen to be uniform across the network, all costs are the same, right? All the agents have the same logistic regression cost or the same quadratic cost. What would be the global cost that the network is minimizing? Would be J, right? What would it be had I not normalized? It would be that J times the sum of Qs, correct? Of course, they both have the same minimum, correct? They both have the same minimum. But now, assume I have an uncooperative solution here where each agent is minimizing that, correct? And I have a network solution here where each agent still has that, correct? Okay, now the excess risk here will take a form like this. I'm going to measure how close this estimate is getting to this solution, correct? Whatever this, let's call it O in this case. Okay, because if all the costs are the same, W star will be W0, okay? But here, here I have to compare the normalized global cost at any agent, right? And see how close it gets to the normalized global cost at the solution, okay? So now, if I measure how close this is to that, this error is of the same order as this to that, because the J normal is exactly the J, right? If I compute the excess risk instead by using the unnormalized definition, the excess risk, this error will be scaled up by an amount which is the sum of Q, right? So whenever I compare the excess risk of the distributed solution to the excess risk of the non-cooperative solution, I always have to scale down by that value for the comparison to be fair, correct? You understand? So if I define my excess risk already in the normalized domain, I can already do these comparisons without having to worry about telling, or remember, this is actually scaled up or scaled down. I have to rescale it before I can compare, right? That's all. That's the reason, okay? So if I know, okay, so that's why for the excess risk, if you see here, okay, for the excess risk, I want to know how far my cost is from what the best it can be. But which cost? The normalized cost, that's all, for the excess risk. So that when I compare, okay, with non-cooperative solutions or with the centralized solution, the comparison is meaningful. I don't have to worry about scaling and rescaling, okay, that's all. You understand why I put here? For the MSD, this is not an issue because the MSD, you are comparing W, how close it gets to W. Here you are comparing the cost. So the costs have to be of similar order, okay, not scaled up or scaled down. That's all. You understand now why I scale? Okay, it doesn't change anything, but it makes sure that the comparison is fair. Okay? So you see what the excess risk is measuring. It's measuring on average how close you are to the minimum you can get, right? This is the best risk you can hope for, okay? And this is how close you are going to get to it, okay? You remember that in the machine learning algorithms we studied in 210A, the risk usually was related to the probability of misclassifications, right? Misclassifications. We had approximations for that. We had cost functions that approximated that ideal situation, right? So essentially measuring quantities like this help you assess how close you are getting to the best classification error you can get, or approximate classification error you can get, right? So measures like this are useful in that context. Very good. Okay. Now, the interesting thing, and this follows from a result in the lemma, okay, in the lemma I showed you before, okay, because these are convex functions, the difference between these two convex functions, you can write it as a weighted norm of this difference, which is W tilde, weighted by the Hessian matrix, right? This is a result we proved in the appendix. Okay, here it is. Okay. Okay, I'm just repeating it here. Okay, if you read the notes, you will see it. That difference of costs becomes the error vector. Okay, and it is weighted by the Hessian matrix of the cost. Well, this is the normalized cost, right? The Hessian matrix, here it is. Okay, now, why did I add 1/2 here? Because I'm not using W tilde K, I'm using W tilde extended K, right? Which is because the norm squared will double, right? Because it is the vector and the norm of the other vector is the same. So that's all, just to keep things, right, scaled properly. I could have written here W tilde K and without the 1/2. So why did I put the E? Because the error recursion for the evolution of the network in the general case will always be in terms of the E's. So it will be easier for me to evaluate these norms. And then I scale them by 1/2 whenever I need them, right? So that's why I'm introducing the definitions in the E domain. Fine? These are all trivial things, but I need to remind you so that, and this is the average ER. So these are the quantities we need to evaluate. Okay? So you see here, at agent K, I now added the 1/2 because I added the E. For the network, I'm averaging over all agents. You see, this is now the error across the network, right? This is the sum of all of them. So the sum is already embedded in the way I wrote it. There is no K here. So this already gives you the sum. You divide by N. Because of the E, you divide by 2. And this is what I just explained. So this is over the network, okay? Over the network, you have to, again, average. You see, this is H bar chronicle I. This is because you are going to repeat your H bar, because you are averaging several of them. Each one of them has an H bar. So this is the compact way of writing it. But what's important of all of this is for you to observe the following, right? Whether you are interested in measuring mean square measures or excess risk measures, the important thing is you need to evaluate a mean square error, whether it is with weight I or with some weight here, sigma, right? So the analysis that I'm going to do next, I'm going to be evaluating quantities like this. You see, quantities like this. Okay? For some weight sigma as I goes to infinity, right? I'm going to evaluate a weighted mean square error norm. If you are interested in MSD, you set that sigma to I. If you are interested in excess risk, you set that sigma to some other matrix. You understand? Yes.
Since H involves H case from...
Yes, this is the Hessian matrix, right? This is the Hessian matrix for the global cost, right?
So that means that the excess risk, there's no notion of an excess risk over the network being the average of the excess risk across the nodes. You already have all the nodes.
Oh yeah, this H bar, yes, this, because you see, because here, okay, here, the way the excess risk was defined, okay, it is not how close the individual cost gets to the individual cost. This is different, okay, because this omega star is the minimum for the global cost. So what I'm measuring is how close the global cost evaluated at the individual estimate is getting to that, you see? So now when I approximate this, not approximate it, express this as a weighted norm, it is the Hessian of this global cost that will come up. You understand? Okay? Anyway, these are slight differences in the definition, but you get the idea. Okay? And these are the compact ways of writing these definitions if you just use limits without lim sup and divide by mu and multiply by mu. Okay? Very good. So now, let's derive the main result. This is the main result, okay? Well, part A of the main result. Okay. So what is the main result, okay? So remember this gamma was a number between 0 and 4. Where does it come from? From a condition on gradient noise, right? This comes from the noise, okay? And since it's not gamma that will appear in my expression, something modified, and you already saw why these modified things come up, right? So I'm defining it as gamma m. It is the minimum between 1 and gamma divided by 2. This is different from the other gamma you saw, okay? This is what will come up in the final expression. So I'm defining it, okay? But it will appear for the same reasons that you saw before. You will have 2 powers of mu. Which one dominates will depend on how gamma compares to 1. So let's define it like. So this gamma m will come up, okay? So it doesn't matter. This gamma m is just a constant, okay? It's just a constant, okay? The important thing is that it is strictly positive. This is the important thing, right? Because gamma is strictly larger than 0, right? It's less than or equal to 4, but it is strictly larger than 0. So this gamma m is strictly positive, okay? That's the important thing to keep in mind, okay? So what is it that I'm going to show now? I'm going to show these 2 results. Actually, I'm just going to show one of them and the other will be very similar, okay? Okay? What I'm going to show is, remember this expression? This is the mean square error at this is the mean square error of W at node K, right? The E and the 1/2 is just for convenience, right? If I can find this lim sup, right? I can then scale by 1 over mu. I'm going to show that this is equal to something, correct? Equal to something. So let me explain the result and then we'll do the algebra to show that this is the case. I'm going to show that it is equal to something. Where this term here I'm going to show is proportional to mu. You don't see the mu there now, but you'll see it once I'm done. This gamma, I told you, the important thing is that it is strictly larger than 0. So this is a higher power of mu. Okay? So now, when I divide by mu, the mu that's hidden here will disappear. The rest will become a constant. But here you will still get mu to the gamma. And then when I take the limit as mu goes to 0, this will disappear, right? The constant term will remain. Then multiply again by mu, you recover this. So this will end up being your MSD, correct? Okay, so showing this is an intermediate step to showing that this is the MSD that I'm looking for. I'm going to tell you what this X and J are, okay? Fine. I mentioned to you before that the quantity that you will get is a combination of P, H, and G. They are hidden here. You don't see them yet. Because the next lemma, that's why I told you this is part A. Part B of the result, okay, is to show that this can be written as a combination of P, H, G. And then that concludes the argument, okay? So this is an intermediate result, okay? Understood? Okay, and then this is, of course, this is the entire network, so you have to divide by n, okay? So this is the MSD for an individual agent, this is the MSD for the entire network. So what's the difference? There is a matrix J here. Okay, what is this J? This J is a block diagonal matrix. It will have zeros, I at the location corresponding to the agent. That's all, okay? Because this X is a big matrix, you're going to see. If you want to extract from it the performance of agent K, multiplied by this block diagonal matrix where you have an I at location K, that will extract the proper information. The trace of that is the MSD. Okay? So the JK is easy to define. Okay, what is the X? Okay, so here it is. Let me show you the definitions, okay? So I'm going to show that these expressions are given by this. H, you know, is 1 or 2 depending on whether your data is real or complex, right? So this is general, okay? The rate, and not only that, I'm going to show you that this error is going to approach that because this is a limit. At what rate it's going to approach that limit? The rate of convergence. I'm going to show you that the rate of convergence is given by this expression. So this is the sum of the QHs, positive definite, minimum eigenvalue of that times 2, 1 minus that, okay? The important thing is that this Q is of the order of mu. You already know this Q has mu in it. So this is of the order 1, it's 1 minus order of mu. The convergence rate is 1 minus order of mu, but that's the expression. So what is X now? Okay, X is the solution to a Lyapunov equation. Okay, I'm going to show you exactly what it is, okay? But if you remember when we talked about matrix results, I introduced, this is called the Lyapunov equation. Okay, so B is some matrix, B star. If you solve this equation, so B and Y, I'm going to tell you what they are. We saw them before. I'm going to show you the expressions on the next slide. Put them here, solve this equation, which we know how to solve. I will show you. Then this is the X that you need. Okay, so let's put these things together, okay? What are these quantities? Let me remind you. The A's you know, correct? The M you know, step size matrix. The H you know, the Hessian matrices. Right here it is. The S contains the gradient noise. Okay, because you have, each node has one G. Put them into an S. And then the Y has the information about the S, and this information is scaled by MA and MA, A2M, MA2, okay? So it's simply a scaled version of this S. The B you already saw, right? This is the matrix that we showed is this table one, the step size is very small. F is going to come up. I haven't introduced it yet. F is the Kronecker product, the block Kronecker product of B with B star with B transpose. It will come up. Forget it for now, okay? J is what I defined before. You put an identity in the location, okay? So the only thing that's new here that you haven't seen before is the covariance matrix of the noise. It was S. I called the gradient noise S, so that's why I call it matrix S here, okay? And Y is related to S. Fine? Okay, so you see, B you already saw, simply the dynamics, the matrix that determines the dynamics, and Y is the matrix that comes from gradient noise. These are the quantities that go here. Okay, that go here. Now, how do I solve this equation? Of course, you can use MATLAB. It will solve it for you very quickly, but, okay. But actually, the dimensions of this matrix is very large. You can run into trouble even if you do it like that. So I'm going, okay. So for example, this is actually can be transformed into a linear system of equations. I showed you this when we, right? Kronecker products, right? Okay. Because remember this property here that the vec of the product of three matrices A, C, B is what? Is B transpose Kronecker A vec of C, right? Now, if you want to make it more general, you can use B vec. Okay. Vec, you know what, a column, and you put the columns underneath it. You take a matrix and it becomes a vector. B vec, you vectorize this block, and then this block, and then this block, right? So it's block vectorization, block Kronecker. So you can write the result either way. So if you come here and you apply that here, what do you get? Look what you get. You will get B vec of X, right? B vec of X minus B star Kronecker product B vec of X again. Yeah, there is a transpose missing somewhere. Okay. Fine. Is this correct here or did I think it's correct anyway. Equals B vec of Y, correct? You get the idea, right? So now you can group these two things. You see I minus B star transpose Kronecker B vec of X equals B vec of Y, correct? It's now just a linear system of equations. You know Y, you know this, you solve for X, and then you unvec it, right? So the Lyapunov equation is nothing but, okay, of course, because B is stable, this matrix is invertible, so then the solution exists, okay? So that's why at the end of this statement, I give you several forms to find X, okay? So this is one form. Okay, the one I just showed you, I minus B star Kronecker B inverse B vec of Y. I wrote it in terms of the F, okay, F star. So that's the form I just showed you. Well, if you take the trace, if you find the trace, right, you can find the trace of X would be given by this quantity, right, because you can use another property of Kronecker products. Anyway, I'm going to come to that. When I derive these expressions, you are going to see them, okay? the trace of a product, you can write it as a VEC operation as well. That's where this comes from, okay? And the trace of j times x is given by this. The important thing is that you know how to find x, and you know how to find its trace and the trace of j times x. There is another way to find x, which is using a series representation. You know why? Because remember, let's do it. X minus, what was it? X minus bx b star equals y, correct? Plus y. Let's write it like that, correct? Okay. Repeat. Replace this x here by bx b star plus y. What will you get? B squared x b star squared plus by b star plus y. Repeat, right? So if you keep repeating, you see y and multiplied by powers of p will keep appearing, and this first term here will go to 0 because b is a stable matrix. Right? B to the n as n goes to infinity will go to 0 because B is a stable matrix. You understand? So that term will disappear. Fine? Okay? Actually, when we talked about solutions of Lyapunov equations in the lecture when I reviewed matrix results, I talked about all of this. Fine? Okay. So the key thing now is I need to prove this result. Right? And then most probably in the next lecture, I will show you how this result can be rewritten in terms of the P's, the H's, and the G's, okay? So let's prove that. So before I continue, you see, in the previous lectures, I showed you that the lim sup of something like this is of the order of mu. Now I'm being much more explicit. I'm telling you exactly what that order of mu is, okay? Proof. So let's go to the proof. Okay. Have a question? No. Okay. Now, remember what I did last time? I started from the error recursion for the network and I replaced it by a long-term model. And I called the error vector for the long-term model WE prime. Correct? So I wrote here the evolution of the error for the long-term model. For the actual model, it was a boldface B here, which had a boldface H. And I replaced that by a constant B plus an error term, an H tilde. And that error term contributed a C term here that was of the order of mu squared, and we said we are going to throw it away. But we didn't just throw it away. I told you that if I throw it away, the evolution of this error will remain close to the evolution of the true network, and I told you exactly how far apart they are, right? I'm going to use that today. And why did I do that? Because it's easier for us, as you are going to see, to determine the performance of the long-term model. And then I use that difference that I derived last time, added to the performance expression I'm going to derive here, and tell you this is the performance of the original network. You understand? This is the argument I'm going to use, okay? So here all I have the error recursion for the long-term model. This is exactly what I did last time, okay? This is the recursion. I'm just repeating it. Remember what this BE is? Is the vector that contains the individual gradients, right, at the W star. They are not necessarily 0, correct? So that's why you get this bias term here. If all the gradients have a common minimum, then it will disappear. If you take expectation of both sides, you get the last equation. Correct? Because the noise is 0 mean. So you get the last equation. Now, the important thing to observe, B is stable. So if you iterate, this is a constant driving term, right? Okay. If I iterate that recursion, will the mean value go to 0? Right? This is like x equals bx plus a constant. If you iterate it, it will not go to 0, right? If I did not have this term, it will go to 0. But because of this, it will go to what? To I minus b inverse times that. It will go to some steady state value, which is not necessarily 0. So the mean error vector is not asymptotically 0 mean. Correct? It's not. Okay? So I'm going to define a 0 mean quantity, which is the difference between the error and its mean. Okay? Remember, this is a long-term model. This is in the limit, right, as for very large I. Okay? So here, if you go back, if I subtract these two recursions, this minus that is z at time I, correct? This minus that is z at time I minus 1, correct? This minus that will cancel. So you'll find that z equals b times z plus this. So this is the recursion for z. I eliminated the bias term. I'm now going to focus on z. So why is it that studying the variance of z, the expected value of z squared, will give me the answer that I want? Because I'm interested in what? I'm interested in the variance of this, not even e prime. I'm interested in that. Okay? But I know if I replace e by e prime, how far they are from each other. So I'm going to show you next that if I evaluate the variance of z squared, the expected value of z squared, it is related to that quantity, and therefore I can focus on this. And this is easier to work with because I don't have a bias anymore. Okay? So here it is. Well, if your quantity here is the variable minus its mean, what would be the square of that under expectation? It would be the, okay, so norm of z squared under expectation, it will be the norm of w tilde, correct? Minus the square, right, of that norm, this norm. Correct? You see, this is what you have here. You understand? You see, if you have a variable here, let's say you have a variable z scalar, x minus x bar. What is the variance of z? Expected value of x squared minus the mean of z squared, right? This is exactly the same thing. Okay? Are you following? So you see, we already know how big this is. The norm of the mean of the error, mu. So the norm squared is mu squared. So you see, these two things are very close to each other by a higher order power of mu. So if I find this, I can simply add this to it, and I get that. Correct? Okay. But I'm not interested in this. I'm interested in the variance without the prime. But how far apart are they from each other? This much. This is what we proved last time, correct? Now, which power dominates, this or that? Mu is very small. This one, right? So you see that this norm is the one without the prime plus this much. Correct? So if I find the second order moment of z, I can correct it by this much to get what I want. You understand? If I correct it by this much, I get this variance, but if I correct it by this much, I get what I want. Okay? Which is what you have here. So this is why I'm going to focus on z. Because once I find what the mean square error for z is, I'm going to add this correction term to it based on the results from the previous lecture. Right? And then I'm going to get exactly the expression. You see, this is the expression we had in the statement of dilemma, correct? So let's focus on z. Okay? And you see here, right, I already scaled by n and by 2 because this is what I want, right, n and 2. It doesn't matter, right? If I just find that, I can always scale by 2n, okay? So how do I do this? Well, remember I have a recursion for z. This is the recursion for z. I want to find what the variance of z is. But actually I want to find what the weighted variance of z is, because remember, different choices for sigma will allow me to tell you what the MSD is, what the ER is. So let's do it generally, right? Okay? So how do I do that? Let's square here, weighted, right? So z star times sigma times z will be this star times sigma times z, the second term star times sigma times z. What about the cross terms? The cross terms under expectations will be 0 because S is 0 mean and independent of the rest. Correct? Are you following? Okay? Okay? So this is exactly what you have here. So I squared, okay? So I'm doing it first conditioned, and then I take expectation again and remove the conditioning, right? So when I square, okay, you will get this is squared with weighting b star sigma b. You see that? Where it came from? Because it was b times z, so the star of that becomes z star times b star times sigma times b times z. So it's like a weighted norm with b star sigma b. Okay? Here it used to be A transpose ms. So the transpose of that times sigma times this s squared, correct? Okay. So now I need to evaluate this, I need to evaluate this. Okay? Now, let's evaluate this. Because we already know, remember the variance, this is the variance of S, right, at any time I. This contains all the S's across the agents, right? Each one of them I know I can approximate by GK plus a correction term. That's what I proved early in this lecture, right? So I'm going to use that fact here to replace this by something that depends on the G's plus a correction term. But the G's, I collected them into the matrix S, remember? So I'm going to show you how this can be written in terms of that matrix S plus a correction term. But that matrix S will appear multiplied by MAAM. That's exactly what I called Y, right? So this term I'm going to show you can be replaced by something related to Y and sigma and a higher order term. Right? That's what I'm going to show. And then I'll consider the second term next. Okay? So let's consider this term first, okay? So here it is, this term first, okay? What's that? You see, this is Si star times the weighting matrix Si, right? This is what this is when you write it like that, correct? The weighting matrix in the middle, okay? And this is a scalar, right? Okay, so a scalar is the same as the trace. Nothing changed, correct? Well, trace of AB is the same as trace of BA, okay? So I can take this SE star, put it here. That's exactly what I did here. Correct? Okay? Why? Because I want to introduce the covariance of S, which I know is related to G. That's why, okay? Okay? Here it is. I know that the covariance for each agent is related to G, right? But this is the covariance of all the S's together, right? Is related to S by this much. And the gamma prime was the mean of gamma 2, correct? Okay. Very good. So now, okay, I need to use this result to find out how much this is exactly, okay? So this is just now some little algebra here, you see? So, this quantity here, okay? So what I did, okay, I multiplied from the left here by this quantity which appears there. You see, that's all I did. Okay? Because the norm of this is upper bounded by the norm of this times the norm of that, correct? The norm of this we already know. This is how big it is. Okay? Mu gamma prime over 2. The norm of this adds mu squared. That's where the 2 comes from. The norm of sigma. But sigma is a Hermitian matrix. Okay, its norm is bounded by the trace. Because the Hermitian matrix, its 2 norm is the largest eigenvalue. The trace is the sum of the eigenvalues, right? So this sigma is actually Hermitian on a negative definite. That's how we are going to choose it. Fine? So all I did, I showed actually that this quantity here minus S weighted by that, you see what I added a 2 because I have M and M, and trace of sigma. You might say, why do I keep trace of sigma here? Why didn't I remove it? Because you are going to see, I'm going to choose sigma and it's going to have an impact here, okay? So keep it, because technically I still don't know how I'm going to choose sigma, okay? So let's keep it, okay? Very good. Well, you see, this is the norm of a matrix, and I explained to you before, the trace of X for any square matrix is upper bounded by a constant, the norm of X. This is a property, a homework problem, okay? This is the norm of the matrix. So I can conclude from this that the absolute value of the trace, right, is also of this order, correct? Here it is, absolute value, and this is the trace. Okay, why is that the trace? You see, this times that is the trace, right? The trace of that, sorry, is this. And then this quantity times S, the trace of that, because you see M, A2, sigma, A2 transpose M, S. So the trace of that. Okay, so I'm going to bring this MA2 to this side, remove it from here. This is what I define to be Y, so you get trace of sigma Y. Fine, okay? So what's the conclusion here? Okay, the conclusion is the quantity that I want, I showed that it is trace of sigma Y, like I stated, plus a correction term. Correct? Right? Of course, the algebra is needed just to make the argument precise, but the intuition, you already had it, correct? Okay, so that's it. You see, so if I come back, this term I already know what it is, right? Here, sorry, this term. So it is trace of sigma Y plus a correction term. Fine? What about this now? We'll come back to that. And the correction term, we know what it is. Sorry, here it is, okay? We know what it is, fine? So, okay, so we showed 75, right? Just to be precise, I showed that the absolute value of the difference is of that order. So the difference is between this quantity plus something of that order, or this quantity minus something of that order, right? If I showed the absolute value of the difference is upper bounded by something, right? Then the difference is between two bounds, right? Minus and plus. So that's where, okay, because, so what I showed then, this variance is this, plus this is the upper bound. So it will be upper bounded by that. It will be lower bounded by this, right? Very good. Okay. Continuing, okay, remember this property. Okay, if I take now lim sup of this side, lim sup of this, here I have the sum of two quantities. The lim sup of the sum has this property. It's upper bounded by the sum of the lim sups, right? So if you do that, okay, so you will get that the lim sup of this is upper bounded by the lim sup of this plus that. And similarly for the lim inf, okay? You're going to see soon where I'm getting with this argument, okay? So, when I goes to infinity, I can group these two terms. That's what I did here, you see? Because I can replace this by zi group with this. The weighting becomes sigma minus that. The weighting becomes sigma minus that. Fine? Okay. Now, what's the point of all of this? The point of all of this is the following. I showed lim inf is always smaller than upper bounded by lim sup, right? So look, I showed that this quantity is smaller than this, which is smaller than that, which is smaller than that. So I bounded the lim inf and the lim sup. Here it is, you see. The lim inf is upper bounded by that. I bounded it from below and above, and I know exactly what that correction term is. I'm just calling it B for simplicity, okay? It's something that depends on mu. Actually, this is mu max, right? Typo here also, okay? Okay, fine so far? Okay. So if mu, okay, as mu goes to 0, right, as mu goes to 0, this upper bound and that lower bound essentially collapse, right? So for all practical purposes, what this is showing is that as mu goes to 0, for very, very small mu, the lim sup is given by that quantity, right? And the lim inf is given by this quantity. And this is what I mentioned to you early in this lecture, that I'm going to show you. I'm going to show in this lecture that the lim sup and the lim inf of the second order moment is some quantity plus a higher order term in mu, some quantity minus a higher order term in mu, and that motivated me to define the MSD by dividing by mu and then taking the limit, right, and then putting the mu back. Remember? So these two expressions motivate what I mentioned early in this lecture about how I define the MSD. It's because of these expressions. That's why I derived them here, okay? We will not use 85, but I wanted to introduce it here so that the definition of the MSD that I introduced earlier on makes sense to you. It comes from these expressions, okay? So let's continue, for example, with 84. With 84, okay? I want to use, remember, what is it that I want to do? I want to find the expected value of z squared. Fine? Okay. I am free to choose sigma. If I tell you choose sigma, what would you choose sigma to be? Sorry? Make this equal I. Choose the sigma that makes that equal I. That sigma, once you put it here, you will get that trace of x. That comes in the lemma. I'm going to show you. You understand? You see, we are almost done. We are essentially done. Once you get to this, you see, this came from where? This came from the variance of the noise, right? Which we already knew. Okay? Now I have to make this the identity. So let's choose sigma. Okay? Okay? So before I get into that, I'm just reminding you of these properties, right? The B vec of a product of 3. I already used it. And what I mentioned before, the trace of a product, you can write it as the inner product between two B vecs, right? B vec of B, B vec of A. Okay. So, okay. And I'm reminding you of Lyapunov equations. I already mentioned that. This is a general form of a Lyapunov equation. That actually this is a linear system of equations. Okay. So Q is Hermitian. If A is stable, it will have a unique solution. We already know that. And that's the situation we are facing. So here I'm just reminding you, right? So if the eigenvalues of A, any pairwise product of the eigenvalues of A does not match 1, which is the case when A is stable, right? By the way, this A has nothing to do with the A from combination policy, right? This is just, I'm recalling a general result here, okay? In our case, A is B, it's stable, so this is satisfied, so X is unique, and you can write it as a series like I explained before, right? Okay? So okay. So that's just a quick reminder, but I already reminded you of that. So here it is. I'm going to pick my sigma to be like this, correct? Okay. Well, this already tells me what sigma is. If I use the B vec notation here, I can find, okay, so if I use the B vec notation, you already know that I minus, what? I minus B transpose, Kronecker, B star, B vec of sigma is B vec of I, correct? So what is the B vec of sigma? This inverse, by the way, this is what I called F before. In the statement of, sorry? Anyway, we'll find it out, okay? But this is related to F for now, okay? That far we know, okay? So B vec is I minus F inverse or F star. You'll see. I think it is F, but we will check. Okay. Inverse time is B vec of I, correct? Well, if you come here and you replace this by what I'm just saying, I minus F inverse, what was it? B vec of Oh, by the way, so the trace of sigma y, I just said, it is b vec of sigma, right? Like this, right? Remember the property I just showed you? Correct? Correct? Okay, so if I put the b vec here, transpose, okay, so it will be I minus f inverse b vec of I, something like that, correct? Transpose times b vec of y. This is exactly the expression I had before for trace of x. Remember? Okay. Do you want me to go back or do you remember? Let me remind you, okay? Because this is important so that everything, remember, I told you that the answer will depend on the trace of x. And I gave you one of the expressions for the trace of x in terms of an inner product. You see here, the I minus f inverse b vec of y is this b vec of sigma that I'm getting. And the other is the b vec of y transpose. Right? You can write the inner product A transpose B or B transpose A, okay? That's it. That's how you get it. Okay? So let's go there. Where is it? Right? So here it is. I'm doing it slowly. So it's F. Okay? She's trying to confuse me. Right? Okay? So here it is. Right? Now put it into the B vec of sigma. Okay? So then here, trace of sigma y, it is an inner product of b vecs. Replace b vec of sigma by that. This is exactly what I called before trace of x. Right? So I derived the result, trace of x. Okay? Now, what's left, so I showed you that the mean squared error is the trace of this x plus something, right? Okay? Because if you go back here, all I did so far, right? All I did so far is show you that this is of the form trace of that x, correct? Now I want to show you two things. That this x is of the order of mu max, right? That it is proportional to mu max. And that for the sigma that I chose, right? For the sigma that I chose, this quantity is higher order in mu. Then that completes the argument, right? That this quantity is of the order of mu to some power 1 plus something positive, correct? These are the two things left. That this x is of the order of mu, and this is a higher power in mu, right? Fine? So this is what I'm going to show next, okay? The argument is not difficult. Yes?
While choosing sigma, why didn't we just take the b star sigma, b star, b star sigma b to the other side and then just...
What did you say?
No.
Here? Here?
I was trying to see if there is a simple solution for sigma.
For this sigma?
Yeah.
I'm solving a Lyapunov equation, right? So I showed you how to transform it into a linear system of equations. You get that solution, right? You can. Okay. Now. Okay, so let's look at that term first, right? That term. Show that it is higher order. Well, all I have to do is add, this is the trace of sigma, right? The trace of sigma, okay? Which I just, the trace of sigma, this is the trace of identity times sigma, right? So I can write it as the inner product of two b vecs, right? So that I can introduce the b vec of sigma, okay? But remember the entries of I minus f inverse, I showed it in a previous lecture. The entries of I minus f inverse were of the order of 1 over mu, right? Now everything comes together now, right? 1 over mu. So this will contribute something of the order of 1 over mu. The 1 over mu cancels one of these ones, so you still have 1 plus something positive. You understand? Okay. Okay. So I do the argument more slowly here, but you get the point, okay? Okay. So let me remember what I'm doing here and why I'm doing it this way. Yeah. I think the argument I just mentioned is simpler. Here I'm doing it more explicitly. I'm taking the I minus inverse, expand it in Taylor series. Each f is that. So then this quantity that I have on that side, which I want to show, oh, sorry, because there is the y. I forgot about the y, okay? No, I already replaced the y. Is there a y? Oh. This part is okay. This is of the order of 1 plus something. I'm now showing the second part, that the x is of the order of mu. Okay, I'm showing the second part, okay? I told you that I have to show two things, right? Where is it? That this is of the order of mu to some power 1 plus something. I showed you the, but now I still have to show that this is of the order of mu. Okay, remember what this x is. Okay, so that's what I'm showing next. Okay, the x is this. Okay, the x is this. So the way I'm showing that it is of the order of mu is by expanding it. This is one argument. Of course, there are other arguments. Okay, because you see I minus f inverse, I can write it in terms of powers, right? This is like a geometric series, but for matrices, right? Okay, replace each f by this, and then, so if you replace the I minus f inverse by this sum, what will you have? You will have, for example, the first term B transpose Kronecker B times the B vec. Then you apply the Kronecker product, right? This becomes what? This becomes the vec of the product, right? Of three, so each one of these will become a B vec, and then you have an inner product of two B vecs. That becomes a trace. So just apply the properties of these Kronecker products backwards, okay? Backwards. Then you can show that these quantities that appear in your expressions can be written like these traces, okay? Can be written like these traces. But you know, an argument, looking at it right now, I can get this more directly as follows. What is this? What are the entries of I minus f? They are of the order of 1 over mu. That's what we showed in a previous lemma, right? Okay. So here I may have forgotten of that lemma. The entries of y, what are they? Remember, y is a times m times s times m times a. It has m squared in it. So it's of the order of mu squared, right? The order of mu squared, the order of 1 over mu. So this term will be of the order of mu, right? That's a simpler argument, okay, than what I have here. Okay, here I'm not using the result of that lemma. I'm just doing it from first principles, okay? I'm doing it from first principles, okay? So the way I'm doing it, so this is the x, for example. Then I'm showing you that because, sorry, this is the trace of the x, but this is the solution of the Lyapunov equation, right? So that quantity x is the solution to a Lyapunov equation for the second term, okay? So I have two matrices there. Each one of them is the solution to a Lyapunov equation, and then I show you that the entries of these matrices are of the order of mu, okay? Anyway, but you get the idea, okay? If you are interested in following this argument, which does it very slowly, you will get to the same conclusion. I justified it, I believe, more quickly, okay? By using the result of the previous lemma. It appears when I was writing this, I forgot about that lemma, okay? But you get the idea, okay? So this we showed already, right? And this will come down, okay? And this trace of x, oh, here is the lemma, okay? Okay, that I minus f inverse is of that order, okay? So this simplifies the argument, okay? Simplifies the argument, okay? So here it is, for example. I already have it here, actually. Right? Because this is of the order of 1 over mu, then you get 1 over mu, okay? Anyway, these arguments are simple. I don't need to, okay? And then, okay, if the norm is of the order of 1 over mu, then the trace is of the order of 1 over mu, okay? You all agree with this, right? I already explained the intuition. This is not difficult to believe. But what I need is the trace of it to be of the order of 1 over mu, because it is the trace that comes up in the expressions, right? So the way I do that, okay, this is how I do it. You see, so x prime is a matrix, correct? This is x prime. B vec of x prime, what do? Okay, it is a block matrix. You vectorize each block, put them on top of each other, and that's the norm of this big vector, correct? Okay, so let's consider the blocks that are on the diagonal, okay? So look what happens, okay? So the trace of the matrix is squared is the sum of the diagonal elements of the matrix squared, correct? Now, and I'm collecting these diagonal elements into a vector B. Okay? So of course, this inner product is the sum of these entries squared, okay? By Cauchy-Schwarz, this is upper bounded by the norm of 1 squared, okay? The norm of B squared. Let's assume that this matrix is of dimension L, so this is L, norm of B squared. But now, this vector B contains some of the entries of x prime. Obviously, the norm of B is much smaller than the norm of the entire, right? So there's simple argument, and you get to the same conclusion here, okay? Fine? Okay, so concluding that the norm is of the order of 1 over mu is simple, and then a simple argument will show that the same thing extends to the trace, okay? So there it is. Okay, I already gave you the intuition earlier. Okay, so the intuition I gave you earlier is a shortcut to this argument. Okay, you don't need to go through all these steps. It's a shortcut. Okay, so this is that, and this trace of x similarly is of the order of mu. I explained why, right? Because this will have I minus f inverse b vec of y, b vec of I. B vec of y contributes mu squared, I minus f inverse 1 over mu. So the norm will be mu. And then you use a similar argument to conclude that the trace is mu. So this first term is of the order of mu. Okay? Fine? Okay? So that's it. Okay, and then I group, right? Okay. Now, but I want to go to this domain. How do I go from this to that? I have to add mu max 3/2, right? And now you have to make the argument which one of these dominates, right? It depends on how gamma prime compares to 3/2, correct? The same argument I showed you before will lead you to this conclusion, that the result is this plus this correction term where gamma is the gamma m I showed you before. Did you follow? Right. If you think about it, the argument is not very difficult, but it has some algebra, right? The variance of z is the sum of two terms. The variance of the noise, right? It's a recursive relation plus the variance of the noise. The variance of the noise, we were able to bound it very quickly by the trace of sigma y plus a correction term. And then the recursion, we chose sigma to eliminate the weighting, right? Okay. And then we were able to write it as trace plus something, and then we showed that this something is the power 1 plus gamma of mu, and this something is of the order of mu, right? So that now if you continue the argument, divide by mu and multiply by mu, which term will remain? This term, okay? Did you follow? Do you get the idea? Okay, so the last few slides where I go through, you know, what you see in red are typos, okay? Okay, now, the last few slides where I go through Taylor series expansions, these arguments could be simplified if you use the intuition I explained to you. If you remember this result to bound the norms, and then use the simple argument I showed you to transform these bounds on the norms to bounds on the trace, and then that concludes the argument, okay? It's as simple as that. Very good. Okay, and now you can repeat. I'm not going to do it. If you are interested in the performance of a single agent, not the entire network, how do you extract the performance of a single agent from this big vector? This vector contains all the W tildes. If you compute this weighted norm where this J only extracts the kth entry, this becomes W tilde KIE, correct? Squared, right? So all you really have to do is, this was the trace of x, but with weighting it becomes the trace of jx. That's what it is. That's why the J comes up when you are interested in the performance of a single agent. Okay? Now, the only thing that's left is the convergence rate. This is quick, and then I'm going to conclude here, okay, so that the remainder I'll continue it next time. So the only thing that's left is at what rate I'm going to go to that value. That expression, the trace of x or trace of jx, is still not very useful for us. Next time I'm going to simplify it in terms of the p's, h's, and g's. That will become useful for us, okay? That's why I told you this is part A. Next time, a small argument will make it into part B, okay? And then that will conclude the argument. What's left is how fast. Remember, this is the recursion, right? I showed you that the variance at time I, the variance at time I minus 1 with weighting, and we chose the sigma, trace sigma y plus a correction term. And then we chose the sigma to help us evaluate the variance, right? If you want to get the excess risk, you choose the sigma differently, right? You just choose the sigma in terms of the h, right? And you will get the expression for the excess risk, which I have also, okay? Now, I want to know at what rate the variance of z is going to steady state. Well, let's choose here sigma equals I. So it becomes this, correct? Put I here, and iterate, starting from minus 1. You will get equation 112. Is that easy? It's not difficult to see, correct? Because you will get zi squared is zi minus 1 squared b star b. Then zi minus 1 squared b star b will be zi minus 2 squared b star squared b squared. Keep iterating, you will get this power of, okay? Now, if you look at this recursion, okay, as I goes to infinity, this is the trace of x, by the way. This is exactly, I showed you in the previous slides, right, that x can be written in several ways, right? One of them as a sum, infinite sum, right, series. And here you have the trace of it. So this actually, as I goes to infinity, this is the MSD, the trace of x, correct? This is the higher order term. I'm just calling it like that, higher order term, okay?
But now you're using the long-term model to infer something about the same model from time zero.
Sorry? No, okay. So don't think about it as time zero. This is for I, long-term model, very large I, starting from that point in time forward. Yes, maybe I should adjust that, but that's what this is meant to say, okay? Yeah, for I, very large I, okay? Start from very large I and start it. Maybe I should have said for I larger than or equal to some capital I here, and then write it in that form, right? I minus capital I. That would have been the, okay? But you get the point, right? I shifted the origin of times to that point, and I'm iterating from that point onwards, okay? So, to be more precise, I should have said I larger than or equal to some capital I here, and then start iterating from capital I onwards. So here you will get powers in terms of I, little I minus capital I. But what matters is as I goes to infinity, this term will disappear. This is the transient term. This term will go to the MSD. So the rate at which you reach the MSD depends on the rate at which this is going to 0, correct? So let's see at what rate this is going to 0. Okay? At what rate this is going to 0. Okay, so let's look at this. You see, this is z minus 1 star times that times z minus 1. This is the initial condition at this capital I time, right? Future time. Okay? So I can take this z to the other side. It becomes the trace in terms of the covariance of that initial state at time capital I, right? I don't care what it is. It's some value. Okay? Well, the trace of a product becomes what? Inner product of two B-vects, right? And this is the B-vec of the product of three matrices. It becomes that. Why do I write it like this? Because now, this is going down to 0 at a rate that's determined by the eigenvalues of this, right? So what is the spectral radius of B transpose B star, right? Because what you have here is something like this. B transpose chronicle product B star, right? So the spectral radius of this determines the rate of convergence. What is the spectral radius of this? What's the most the magnitude of the eigenvalue can be? It is the product of the spectral radii, right? And it will be the same, rho, yes.
That property that the product of the individual eigenvalues still holds for the...
Yes, it still holds for the chronicle, yes. Okay, you have it in that table I showed you. Okay, I don't know if that table is quick, but I can show it. Where is that table? He asked the question. Blame him, okay? 6. Question 6, okay? I'll go back now.
All the properties. You can assume all the properties.
No, he doesn't believe me, so he has to see it. He saw it now, okay? So it is rho squared, okay? So it is rho squared that determines the rate of convergence. But remember, I gave you what rho of B is last time. In a previous lecture, I told you what the spectral radius of B is. The spectral radius of B is this. So what is the spectral radius of B squared? You square it. But when the step size is very small, right, you can use this approximation. When x is very small, this is 1 minus 2x. So that's why you get the 2 here. You get it? Okay. Well, and then I have an example. Okay, just to conclude, I have an example showing you these results for the mean square error case networks. You know, that's simple. We don't need to go through it. So this is in this particular case. Okay, I'm assuming the covariances are uniform. Okay, so the minimum is the same. Okay. Okay. Yeah, one thing I want, this is, okay. The purpose of this example is just to make the following remark, okay, the following remark. In the mean square error case, okay, in the mean square error case, okay, if the data comes from a linear model, the omega star will coincide with omega 0, correct? Okay. In that case, when omega 0 agrees with omega star, okay, the long-term model and the actual model will be the same. You can go back. This is an example we showed last time when we discussed the long-term model. So you don't have this correction of mu to the 3½ that you need to work with. So when you derive the performance of the algorithm, at some point, if you remember, once I derived the MSD of Z, I added mu to the 3½ to get the MSD of the original network. You don't need to do that. You can continue with the error that you had there. That error that you had there was mu squared. So what I'm trying to say is that for MSE networks, this term actually will be mu squared, not mu to the power 1 plus gamma m. It will be a smaller value. You understand? Okay? Because for mean square error networks, I don't need the correction by mu to the 3/2. If you go back, you will see that. Okay? And we mentioned that's the purpose of this example. Okay? Very good. Okay? Yes, all I'm saying is that for the mean square error case, 1 plus gamma m is actually 2. Okay, is actually 2. Okay, that's all. Okay, and actually, if you go back to the way we defined gamma m, okay, and what the gamma m is defined in terms of gamma. Okay, and for mean square, we know what gamma is. I believe it is 2. So if, the expressions already take care of that for you. Fine. Very good. So I'm going to conclude here. Next time I'm going to take the expression and tell you how do you simplify it. That's what these slides will be doing to get the expression that we will be using. Okay? So I'm going to stop here today.